Hello, welcome to EEE 117. This is Dr. Stoop, and here we talk about Chapter 13, Laplace Circuit Analysis, Laplace Transforms, and this is the second session. So we'll go down. I think we last left off about right here. Okay, so summary last time, we're talking about individual circuit components and how to put them together in a main circuit and do circuit analysis, whether it's be mesh, node, source transformation, Thevenin norm, whatever you want, right? So this is basically how you use circuit analysis. Now, we're going to go a little more in depth today and talk about where and why we use circuit analysis. So very common in electrical engineering, or honestly anywhere in life, you're going to see, as scientists see this all the time, you're going to see something on the ground. You're going to see an object. And you're going to do something to it, and then you're going to get a response, right? You doing something in a circuit is the input. The object you're manipulating or the circuit you're manipulating is the system. And then what comes out is the output, right? So you see a system, you see a button, you press the button. You're the input pressing the button. The button does something, and out pops some food. Right, as a vending machine. Okay, so you're the input, you put money and you press a button. The vending machine is the system and pops out the drink. That's the output. So all of circuit analysis is typically based on the input, the system itself, the circuit, and the output. Those are the three major components. Now, a lot of times in circuit analysis, you might be given a circuit in a black box, meaning somebody comes to you at the shop and say, I have this device, I want to know what it is, or it's not working. What can you do? And it's a closed box. You don't know what's inside. Okay. Now, if you're smart with you could test the input and do several tests. You might be able to notice and see what the output's going to be. And between input and output, you can probably figure out what's inside the circuit. Sorry. Okay. So this is called black box analogy, where you have an unknown circuit called H of T. You have an input to the circuit called X of T. That's us bothering the circuit or testing it. You have an output of the circuit that we observe. And between these, we have a complete system. Okay, so X of T, input, H of T is the system or the circuit itself. Y T is your output observed. Okay. Now, here's an example, is we have a car audio system. Okay. You have the actual music player that you input. You could change the songs, increase, decrease the volume, right? You are the input to the system, okay? Somewhere in your car, you have an amplifier. The amplifier is the circuit that will take your signal and transmit it to several speakers, amplified in power. So the amplifier is the system. That's our H of T. Okay, X of T is the input in blue. H of T is the amplifier circuit, and the output of the whole system are the several speakers in your car or your house or wherever this is. Okay, so this is kind of an analogy of or an example of what these three major systems are. H of T is the circuit itself, the amplifier. Right? We don't know exactly how the amplifier is constructed inside, but we do know if we have an input X of T from the music player, which is a low power small signal from the music player, the circuit will amplify to a high power enhanced waveform to the speakers. So there's an amplification unit in here somewhere. Okay, and honestly, as long as I know the input and I know my output, I could use this black box without even knowing what's inside it and keep going on with my life, right? So not everyone in electrical engineering, you're gonna have to know every single device. Like, for example, I'm in power engineering. I use electronics and measurement multimeters all the time. I don't know how the multimeter is wired inside. I know what X of T is. That's me putting in signals from down measuring. I know Y of T is the digital output of the voltage I'm reading. So then I'm okay with this. I have a good idea of what the middle part, the H of T is. It's a multimeter, right? And through the deduction of knowing X of T and Y of T, I could figure out what H of T is to a certain degree. Okay. And that's kind of the idea of what we're talking about today, right? Is as long as you know two or three of these, you should be able to figure out the third one. Okay. Now, formally, this relationship is called a convolution in time, where your output yt is negative infinity to positive infinity of the actual function inside the circuit, h, times your input. So the x of t is going to multiply h of t, and we're trying to figure everything out. And then we're going to have some time shifting all over the place inside. Okay. Now, this is the harder integral. A lot of people really hate convolution. And I agree with it. But the idea is we always want to get away from integrals as much as possible. So we can use Laplace transforms to take this type of integration and make it easier. So as long as we take the Laplace transform x of t to x of s, Laplace transforms of h of t to h of s, we'll get the Laplace output y of t in h and y of s. And you learned last time how to convert the circuit if you have a circuit. Okay. So instead, let's do everything in Laplace domain and analyze this black box. You have x of s goes into the unknown circuit h of s, and the output is y of s. Right? And as long as you take the Laplace transform of each unit, you'll be okay. Okay. So x of s is typically a voltage source we put into the circuit. H of s is typically a combination of circuit elements and a prearranged degree. And a y of s is usually a voltage reading or a current reading that comes out. Okay. And remember, Laplace transforms takes integrals and convolution and turns into algebra and arithmetic, which is obviously much easier. So instead of having a long integral before, we could relate these three functions as just literally the circuit h of s is equal to your output y of s divided by your input x of s. So this is nothing more than the gain of the circuit. Okay. So all you have to remember is h is equal to y divided by x, or the circuit, the gain of the circuit is equal to the output over the input. Now, as long as you know 2 out of 3 of these, you can figure out the third one. So if I know y of s, so if I know x of s and h of s, I know the input, I know my circuit, I can easily figure out the output. You've been doing this since engineering 17. Okay. Now, if I know the output and I know the circuit itself, I could reverse engineer the input pretty easily as well. Now, the third one is a little bit harder, but still possible. If I know my input and I know my output, I can use something called circuit synthesis and then figure out a circuit that will do exactly what the gain of y of s over x of s is. So as long as I calculate this right here, y divided by x, I will have a function of a circuit, h of s, and we could go into the parts bin and physically build this circuit. Okay? We could reverse engineer any equation back to resistors, inductors, and capacitors on a circuit board if we're good enough. Okay? So 2 out of 3 of these components is all we need to know everything. Now, typically in circuits analysis where we're at now, you would typically be given x of s and h of s. So you're given an input voltage source. We already know the circuit, so calculating the output is pretty straightforward. Okay, but the other two having an output and having a circuit, finding an input, that might be more advanced on the towards your senior design and blah blah blah. I mean, senior design probably involves you building a circuit in the middle, right? So I would tell you what the input is. You already know what the output should be. And it's your job to make the thing in the middle. That's circuit synthesis. Okay. So let's see all this. Let's see this in a writing, an example. So you have a very simple. Always do the simplest circuit first to understand what's going on. We have a voltage source. We have 2 resistors, and we want to find an output across R1. Okay, 10 and 5 ohms. What's our input? The input X is S, it's just this voltage source. Whatever this voltage source is, that's our X of S. Our H of S is the function of the circuit. Now, I know my output Y of S is across a resistor, V out. So from the circuit analysis, if I want to find my voltage V out in terms of the input, what's this ratio? Well, that's just basic voltage division. It's R1. If you want the voltage across the resistor you're at, you put R1 at the top and you divide it by both of them added together, R1 and R2. So you do this 10 over 5 plus 10, 10 over 15 is 0.67. So the gain of the circuit is 0.67. Now, what does that mean? My output voltage, V out, is equal to H of S, which is 0.67, multiplied by X of S, which is your initial voltage, which is what we have right here. Y output is equal to X, the input, times the gain of the circuit, H. Okay, which in this case is the voltage divider with where 2/3 of the voltage go to R1. Okay. Now, this output or this gain, this H of S is unique only to this circuit. If you change where V out is or you change any of these resistors, you're going to have to recalculate H of S. Okay. So once you have the circuit built, this is unique only to this circuit. Now, to show you that, let's swap where V out is. V out is going to be across R2 now. So we will have to go rebuild the system. Still, our input is X of S. We know that that's V. Our output Y is always equal to our input X times the circuit gain H. Now the circuit itself, our voltage output is across R2. So now our voltage division is R2 over R1 plus R2, which is 5 over 10 plus 5, which is 5 over 15, which is 0.34. Rounded, of course. Okay. So now our output, V out, is equal to 0.34 times V. Previously is 0.67. Okay. So you can see it changed because our output changed. Okay. So anytime the circuit changes, you're going to recalculate your gain of the circuit H of S. Okay. So this is honestly, this is just a fancy way to say input equals gain. Sorry, this is a simple way to say output is equal to input multiplied by gain. That's all it is. Okay. Now, obviously, we could get, let's say this is the comparison, right? So let's compare the two circuits. Output on R1, output on R2 for the second one. How did the output change from one circuit to another? By moving V out over, the output voltage changes, the gain of the circuit changes, the H of S changes. H of S change because output is on different resistors, so H of S parameters change as well. Okay, so it's very key to know that when the circuit changes, you have to recalculate everything. Okay, now that's obviously the most simplest one. We could go a little step further and get more complicated. Now let's look at an RL circuit. You have R and an inductor, S of L. So what's our input? Again, input's voltage source, V. What's the output? The output's across the resistor. So what's the gain of the circuit? It's going to still be voltage division, except we have an inductor. So the voltage division is going to be across the voltage, the resistor we're measuring. So it's R1 divided by both of them, R1 plus SL. Plugging in R equals 10 and L equal 1, we got 10 over 10 plus S. Our H of S, our gain of the circuit is 10 over 10 plus S. So our output, Y, is going to be equal to the gain of the circuit, which is 10 over 10 plus S, multiplied by the input voltage, V. Okay. Now, again, if these numbers change, or this circuit changes, this all needs to get recalculated. Okay, so coming over here, notice we swapped the voltage off across through an inductor. All right. Do the same thing. Input is still V from the voltage source. Now our gain changed, right? Our voltage across an inductor, so impedance inductor is S of L, so that goes on top. So S of L divided by both the resistor and inductor added together, R1 plus SL, which is equal to L is 1, so we have S divided by S plus 10. So now our H of S, our gain of circuit, is S over S plus 10. Our output now will be equal to H of S times X of S input, which is S over S plus 10 times V. Okay, now this is a little bit different because notice for this circuit, we have an extra S on top because we're taking the voltage across an inductor. Previously, it was a 10 because we're taking off the resistor. So as you see, it does change, right? Swapping your voltage from one spot to another changes the circuit a decent amount, right? How did the output change when you move from one circuit to another? When V out moved, the output voltage changed drastically. Putting an extra S is a big deal, right? Because now it's another frequency variation in your output. How does H of S change? V out change in location, change the voltage divider equation, right? Note that extra S was added for V out on an inductor. So that just means for this one right here, as the frequency changes, there's still going to be a decent amount of change here. Okay. But if you notice, they're both S divided by S. So as frequency gets really big, it doesn't matter anymore, right? As the frequency increases, let's say S is 10,000. You have 10,000 over 10,000 plus 10. This is equivalently 1. So the output voltage is the same as the input voltage. But if you go over here, what happens when S is equal to 10,000? You have 10 over 10,000, your output voltage is 0. So you can see there's a very drastic change in the circuit topology. One has a higher voltage and one has 0 voltage when the frequency is high. Okay. So you see it changes a lot. Okay. So we did a circuit where we had a resistor and an inductor. I want you to do the same idea with a resistor and a capacitor. Okay. So follow the same kind of pattern we did for the example. You have your input voltage. So X of S is your input. H of S is your voltage divider here. Y of S is your output, which is your X of S input multiplied by your gain H of S. Okay. And do the same thing again, except we swap where V out is. See, V out is on the capacitor. So you're going to do it again. Obviously, the answers aren't going to be the same as the inductor one because it's a capacitor now, but it's going to be the same process. Okay. So let's go ahead and take our 15, 20-minute break. Good luck with checking this out. Do your best, and we'll come back and see how you did and check all the answers. So see you guys a little bit. Hello, welcome back to Triply 117 on chapter 13, part 2. We're back for our 20-minute exercise, and let's go ahead and check out what's going on. So remember, there's 2 parts here. The first part is we have an RC circuit where your V out is across a resistor. Let's figure out our transfer function. The input first is X of S is the voltage source. The transfer function, H of S, or the gain of the circuit, is the voltage division between a resistor and capacitor, except the resistor is where the voltage output is going to be. So on top is you have the resistor, which is what we're trying to get the voltage across, divided by both of the components added together, R1 plus 1 over SC. So we have to kind of multiply both sides by S to get rid of the denominator S. So we're going to have S times R divided by SR plus 1 over C. Get rid of the R's by dividing R in both top and bottom. So we have S divided by S plus 1 over RC. This is the gain of the circuit right here, or the transfer function, H of S. We can plug in RC. R is 10, C is 0.5, so you have S divided by S plus 0.2. And your output, Y of S, is V out right here, where the gain is the H of S times X of S, where H of S is S over S plus 0.2 right here, and the input is multiplied by V. Okay. You can do the same thing for the next circuit, except V out is across a capacitor, so that obviously will change things. So again, input is still the same, voltage V. The transfer function H of S, which again the circuit, is the voltage division across the capacitor and resistor, where we're taking voltage off the capacitor now. So it can be 1 over SC, which is impedance of the capacitor, divided by R plus 1 over SC. Divide by, we don't like S as a denominator, so we're going to multiply S on both the top and the bottom. So the S cancels here, the S cancels here, and the R times S pulls over right here. We don't like coefficients in front of the polynomial, highest order polynomial, so we should take this R out. So we're going to divide R in the bottom, divide by R in the top. So you can have 1 over C times 1 over R, so you can have 1 over RC. Same thing over here, you have 1 over RC of the denominator, and then you're going to add the S because the R canceled out. So you have totally, you plug in the 10 ohms and capacitance 0.5 farads, your total transfer function gain is going to be 0.2 divided by S plus 0.2. Okay. Now, again, your output V out is going to be across a capacitor. So it's the Y of S V out is going to be equal to H of S times X of S, where H of S again is 0.2 divided by S plus 0.2. So the gain of the circuit times your input V. Okay. So that's typically how you would do some basic circuit analysis. Again, big trick here is once you have the circuit built and you're not going to change in components, you could just rely on this over and over again to do your calculations every time you use it. Okay. So how can we use transfer functions to find answers, right? So obviously we could do a lot of work building circuit, analyzing it. So we got all the modeling math done, but what do we really care about at the end of the day? How much the output actually changes. I mean, that's the end of the day. I need to know when I do input 1, 2, 3, 4, 5, what is my output? Because I need this equipment I'm going to use to be predictable. I don't want an unpredictable piece of equipment because then I can't use it to my benefit. So we need to make sure that it works correctly into our favor. When we do circuit design, we're going to look at two major things. We look at magnitude and phase angle. We have a voltage source we're plugging in. It's going to be AC with a frequency. What's my output voltage? What's my output phase shift? What's my magnitude and phase shift? It's very, very important. Okay. So if we modify any of these values, do we get a different output? So if my input voltage changes, if my input voltage magnitude changes, or phase angle changes, or my frequency changes, right? What comes on the output? Well, if an input magnitude changes, I expect my output magnitude to change. And we've been doing that since engineering 17. One thing that's new we've never done before is what happens when the frequency changes. If my frequency changes from 100 hertz to 200 hertz, what changes? Well, normally you'd have to redo the entire circuit problem all over again. But because we have this cause and effect, this H of S function, we can figure it out quicker. We know most likely that when input frequency changes, because there's capacitors and inductors, your output will probably change as well. Your magnitude is going to change and your phase angle is going to change. And these are the two we really need to keep track of. Okay. Now, there's going to be some obvious extremes we want to check. Any AC circuit that has frequency modulations will have an upper boundary and lower boundary. So if I take my frequency and go from 0 hertz all the way to 10,000 hertz, there's going to be some edges where I can't change it anymore before the circuit doesn't either explodes or it doesn't do anything anymore. Okay. So at the two extremes of the circuit, either the output goes dead, so you have 0 magnitude, or the output maxes out to we have the maximum power the circuit allows. Those are the two extremes. And somewhere in the middle is between 100% and 0%. Okay. And the big thing is we want to know how that range works. Is it linear? Is it non-linear? Where does it cross over from low to high? Those are all very important things we need to learn about a circuit. Right? Again, what do we really care about? The middle. This is where we can control the output to our desire. Basically, it's volume control, right? Somewhere, when you're at your house, or your car, you have volume control. There's a point where you turn it down so much and it just keeps clicking, but you don't hear anything, right? I mean, there's at some negative like 50 or 60 dB, you're not going to hear anything anymore, right? So turning it anymore is not going to change because you can't hear anything. That's your lower boundary. The upper boundary is where you crank it up so much that your speakers bottom out. So no amount of cranking anymore is going to make your speakers work anymore because they hit their maximum limit. That's your upper boundary of your volume control. So it's very good to know that because you want to make sure that your circuit 1 is still on, you're listening to music. And number 2, you don't go too high and blow out your speakers. You got to go buy new ones, right? So that's why we need to know those mins and maxes. Mainly the max is the most important because that's the one that damages the circuit, right? So how do we figure it out? Well, if we have a circuit and we know what it is, we need to do something called a frequency sweep. So in the lab, when we're designing a circuit, either on modeling through software, or we physically have the device and we're going to do a physical test, we need to do something called a frequency sweep. We're going to have a function generator like you have in the 117 lab, and we're going to crank it down to, let's say, 10 or 100 hertz. And we're going to go 100 hertz. We're going to take a snapshot of the circuit, see what happens. We're going to crank it to 200 hertz. We're going to take a snapshot and see what happens. Do 300, and we're going to do every interval as much as we want, and we're going to see a pattern arise. And that's what's very important. Okay, so we're going to go from the lowest frequency design we need to the highest frequency we need, and we're going to see what happens in the middle. Okay, so that's what a frequency sweep is. Sweep from the lowest frequency to the highest frequency. We need to figure out what are the extremes of the circuit, right? When does everything go to all maximum? Where do things go to all zeros? Because it could be bumpy. It could be up and down a few times in between, depending on your circuit setup. Okay, we need to find that. So first off, we need to find that transfer function. We need to figure out all our roots. Within the roots, there's something called poles and zeros we'll talk about in a little bit. Those will be telltale signs to see what will happen in the circuit, right? How often do we stop to check the circuit? That's another big thing. What's our called sampling rate? Okay, if I want to go between 1 and 10,000 hertz, do I do 0, 1,000, 2,000, 3,000, 4,000? So that'll be what, 12 points or 10 points from 0 to 10,000? Or do I do every 100 hertz? That'll be 100 points, 100, 200, 300, 400, 500, all the way to 10,000, right? Or do I do 10 hertz intervals or 1 hertz intervals, right? The sampling rate is how often you're polling to get information. Now, obviously, if you poll every hertz, you're going to get a lot of information. You're going to have very, very detailed, very accurate graph, very precise knowledge of what's going on in the circuit. But the second question is, do you want to sit there and do it 10,000 times? Probably not. So there's a middle ground, right? You don't want the sampling rate too small because it's going to take forever to do all the work. But you don't want it too big because then you're going to lose information. Okay. Well, let's kind of see what a frequency sweep will look like. I keep talking. The best way to figure it out is do. From the previous circuit, we know our transfer function of the circuit H of S, which is the output over your input, is R divided by R plus SL. Now, I keep talking about S like this mystery variable we've always seen, we never learned about. Here, we're going to actually put it into practice. You can set S as JW, where this W is your frequency of the circuit in radians per second. So my frequency, you take F times 2 pi, that's going to be omega. You can plug it in, and you're going to get an output. Okay. So this literally S, we're going to plug JW, and we're going to plug 100 hertz in here, and we're going to hard crunch this every time. Okay. Now we can check the behavior by increasing omega every increment. Okay. And the way I like to do it is I like to draw a chart out like this. Okay. So notice, remember our function, 10 over 10 plus S. This is what we're going to look at. We're going to look at two things. We're going to look at magnitude and phase shift. Because remember, this S is going to have JW in it now. Okay. So here, let's start low. Let's start at J equals 0.1. So my SL here is now J 0.1. I'm going to plug it in. I'm going to have 10 divided by 10 plus J 0.1 right here. Let's take the magnitude first. So here you're going to have 10 divided by 10 plus a very small number. You go in your calculator, get the magnitude, the bars on both sides, your output, your gain is going to be 0.999. Almost 1. What's going to be your phase shift? Again, figure your phase shift of 10 over 10 plus J 0.1. It's going to be, you're going to only lose maybe negative 0.1 degree phase shift. So you're only going to have a very, very small phase shift. Okay. So that's at 0.1. We didn't see how much of a change. Let's switch it to J1. So we're going to multiply by 10. Okay. So now let's plug in J1. We're going to have 10 divided by 10 plus J1 right here in blue. Let's number crunches. Magnitude 0.995. Not really how much of a change is there? Not really. What about my phase shift? Well, it's going to be negative 5.7 degrees. That's actually a decent amount of change, but overall, it's hard to see that difference on paper. Okay. Let's go quick. Let's just start adding zeros, right? Let's do J10. Okay. Now J10, we're going to plug in J10 for S. We're going to have 10 over 10 plus J10 right here in green, 10 over 10 plus J10. What's your magnitude here? Go in the calculator, plug this in. Magnitude is going to be 0.707. That's a decent jump. Something happened between these two, right? What's their phase shift? It's negative 45 degrees. Something also changed drastically between these two jumps. See? This is the analysis we're doing. Okay, let's investigate further. Let's do J100. So we're going to plug this in. S of L is J100. So we're going to have 10 divided by 10 plus J100 in orange. What's my magnitude here? Here is going to be 0.099. This is nothing. This is less than 10%. This is 10%. So we lost 9% of our output right here. And look at the phase shift. It's negative 84 degrees. So we almost have a 90-degree phase shift, which is very big. Let's confirm the trend. Let's go to J1000. So we put J1000. We have 10 over 10 plus J1000. Look at our output now. It's 0.009. This is pretty much less than 1%. This is dead. Circuit's dead now. You killed it. What's my phase shift? Negative 89.4 degrees. This is pretty much 90 degrees here. So the big trick here you can see is as the frequency increased, what happened? Our gain of the circuit decreased. Right? Our phase angle changed a lot. Right? And so that's a big difference in the circuit here. Okay. Now let's analyze. Let's say V out is equal to 100. So let's say our frequency is 1 radians per second for the voltage source. Well, I know my V out is 100 times your gain. The gain for 1 hertz or 1 radians per second, 0.995 angle negative 5.7 degrees. There's almost no change. Our output voltage is 99.5 volts. I mean, I lost half a volt. That doesn't matter. There's no change. What about when omega is, or the W is 10 radians per second? Do the same number crunch again, right? Oh, and the voltage is 20 volts. So we change, not only did we change the magnitude of voltage, we changed the frequency. We did both. Where our now V is 20 volts times the gain 0.707, angle negative 45 degrees. Our output is 14.14, angle negative 45 degrees. So in terms of magnitude, we lost 30%. So our gain is about 0.7 or 70%. So we lost 6 volts. That's actually pretty decent percentage-wise. Okay. What if we change the voltage back up to 50 volts, but then our frequency changes to 100 radians per second? We have 50 times 0.099, angle negative 84 degrees. Our output voltage is 4.95. Our input voltage is 50. We lost 9% of our voltage. We lost a lot, right? So you can see things change drastically as frequency changes. Even if the magnitude changes, percentage-wise, it's still a big chunk. And we can always see that with this chart we drew, right? This is why frequency sweep is so big. I've noticed about J10, something changes drastically. Everything outside of it stays the same. But overall, I know my circuit went high, it dipped, and went to 0. And about at W equals 10 is about when it really started happening. Okay? So I just copy and pasted the same numbers from the previous one. So this is nothing, it's nothing different, right? So I wouldn't fill this out on paper and pencil right now. You can fill it out later or copy and paste it if you have a pad. What is the trends that we see? As the frequency increased, we notice our output magnitude decreased. It started at 0.99, 0.995, 0.707, 0.099, 0.00. You can see a pretty drastic decrease, especially at J equals 10. Okay. What about the phase shift? As the frequency increased, we have a more negative phase shift. It started pretty low, but again at J10, we started seeing a big flip. And then it kind of bottomed out at J equals 100. After that, it's not much different. And if you put J to 10,000, it's going to be even less. It's going to be like 0.0009, and this would be negative 899.4. So it's going to be even worse. Okay. But that's the overall trend. And what's important is we can graph this, because then this is what you see in a lot of textbooks. You'll see a frequency sweep in terms of a graph. If you go to Andrew 117 lab, you could do a frequency sweep on your oscilloscope. You'll see a graph like this. Okay. Notice at the lowest frequency, it's pretty high. That means our gain is 1, right? And think circuit-wise what's happening. At very low frequency, what's the impedance of an inductor? it's 0, right? At higher and the impedance is 0, all your voltage on the source is going straight to the output. Okay. Now, as the frequency gets higher, your impedance here gets bigger. SL gets bigger. The bigger SL gets, the less voltage will go in R1, more the voltage will go in an inductor. So as you can see, about 10, if you plug in SL equals, and if you plug S equals 10 and L equals 1, you see they're equal, right? So you're going to have roughly, relatively similar amount of voltages. That's where you get 0.77. Okay. And as the frequency gets really high, the inductive impedance dominates, so the voltage across the resistor is going to be nearly 0. Okay, because the inductor is so big. All the voltage is going to be across the inductor instead. So you notice, look at your gain. It started high at low frequency. It started dipping. And then at some higher frequency, it kind of bottoms out and it's not even worth looking at anymore. So our range that we really care about is between 1 and 100. That's the drastic change we see right here. Okay. So between here and here, this is where we see that drastic change. And that's important for us because we could design a circuit to use this to our benefit. Okay. What about the frequency? I mean, what about the phase shift? Again, at low frequency, we didn't see anything. But once we get to about that between 1 and 100, especially at the 10 mark, notice the frequency changes the phase shift starts changing. It goes from -5 to -85 degrees. So within this band, this is where we get that phase shift, right? And then we bottom out. Okay. Give me 1 second. I'm pretty sure I drew that graph wrong. I could cool. Let me redraw this real quick for you, real time. There's a very small error, and I just want to make sure it's not going to mess everything up. Technically, I don't know why I can't erase easily. Oops. I don't want to, I'm drawing everything too much. Sorry, guys. Actually, let's make this easy. The problem is this should not be at 1,000. It should be right here at 100. So I'm kind of like mislabeling it for you. It really should be about right there. Okay. Let's move this up. Okay, that makes more sense. And technically, I should probably move this up a little bit too. I just want to be a little accurate on the graph. I don't want to cheat you guys out. Okay, so let's move about right here. There you go. That looks a little more accurate. Never saying I'm an artist or anything, but let's be accurate wherever we can, right? Oops. Try that again. All right, there you go. That looks a lot more better. So at 100, we're at -85 degrees. And anything after that, it kind of bombs out at -90 and no one cares anymore. So again, the big difference here is really between these 2 points. This is where we start seeing our drastic change. And again, we could use that to our advantage. That's where we could build a circuit to take advantage of this change. Okay. So what are the breakpoints we call it, or what are the points where you see drastic changes? They're called breakpoints. Well, we can all agree that at J equals 10, J10 is where we see that big inflection point, right? Between 1 and 1 is where it starts, 100 where it ends, and 10 is where it's probably the biggest change. So we say a drastic change about midpoint between these two. We'll say J equals 100 is probably where you can see a big change. Okay, not exactly midpoint, but it's in between the two. Okay, which we call this point is called a break point. This is when we start lowering the output drastically, and it bottoms out. Okay. Now, when we look at function, and now what we had before was very simple function. This is a lot more complicated function. We could do the same idea and ask ourselves, Where are we going to bottom out? Where are we going to max out? The easy way to tell is look at your roots. Okay. If you notice up here, where do we bottom out is when J was equal to 10. Okay. And 10 was also, look at everything, everything else was equal to 10. So that's kind of like, especially at the bottom, you see it was 10 plus J10. That's a root. And as long as the J omega is equal to the 10 in front of it, this is where we're going to have a drastic change. So anytime we have a root like S plus 8, S plus 6, we know we're going to have a drastic change when S is equal to 8. When these two numbers line up, S equals a 6 or S equals a 8 or S equals 5, we know something is drastically changing in the circuit. Okay. So formally, we could take S and we could plug in JW to each of these numbers. Now, we don't have to do the math. We could visually see, I know S plus 8, if I plug in J8 right here, we're going to have, after 8, we're going to start having a drastic dip in your voltage or your dysfunction. It's going to start declining pretty bad, right? Because this J is going to be 8, and then J might be 80, and J might be 800. It's going to dominate over the 8. So this is called the pole. Poles are the roots on the denominator because it'll pull the, I call it's going to make the equation go down very fast. After 8, this function is going to start tanking. Okay, so it's called a pole. If omega starts getting bigger than 8, we know the function is going to start trending. It's going to get smaller. This pole is going to pull the circuit down. Okay, we have another pole at S plus 6. So as long as omega gets to 6 or bigger, this is a second pole that's going to pull the circuit down. So if S, let's say, is at 7, we're pulling the circuit down with S plus 6, but not with S plus 8 yet. But let's say omega gets to be 300. At 300, both of these poles are both pulling the circuit down quite a bit. So your output voltage is going to tank pretty hard. Okay. Now, for every pole that's pulling the circuit down, you might have a 0 on top. So the S plus 5 on the top numerator is a 0. Okay. A 0 is if omega gets bigger than the number it's associated, its root is going to start increasing. It's going to make the circuit, the F of S get higher and higher. Okay. Because if I plug in S equals 500, we're going to have J500 plus 5. That's a big number. It's going to, J500 is going to multiply into 96, and we're going to get like 50,000. See? So it's in these functions, it's a constant fight. The zeros on top are always trying to make the circuit bigger and bigger. The poles on the bottom are always trying to make the circuit smaller and smaller. So it's always a constant fight. Now there's 2 poles and 1 0. So given a long enough time, eventually the poles will win over the 0. Okay, but if we have 1 0, 1 pole, they're going to be equal in fighting. Okay, so that's how I like to think about it, is poles make the circuit, the output go down, zeros make the output go up, and we could choose when this happens. I chose 5, 6, and 8. We could design a circuit. This could be like 10,000, this could be 3, and this could be 6,000. And we could, that waveform we saw, we could modify. We could make it humps and jumps and all over the place to build a very complex circuit, right? And so paying attention to poles and zeros are very, very important in circuit analysis. Okay? And pretty much, we're going to talk about that a lot for the next like 3 weeks. So to summarize everything, we have transfer functions, H of S, which takes input X of S multiplied by H of S to get an output Y of S, where the gain of the circuit H of S is equal to output over input, right? This transfer function H of S is unique based on the circuit design and where you're drawing your output on the circuit. So if the circuit changes, the resistor number, you swap resistors, you change where the output's going to be, H of S changes as well. Okay. Now, as long as the circuit stays the same, we could use the same transfer function and put in multiple input signals of varying quantities of magnitudes and frequencies, and we could do a frequency sweep to figure out what the output Y of S is going to be in terms of output magnitude and output phase shift. And then we can correlate our circuit to poles and zeros to know when the circuit's going to trend to zero, when is a circuit going to go to maximum power or maximum voltage. Okay, and that's the poles and zeros is very important in circuit design. Okay, so that's all I have for today. Thank you for showing up and listening to me talk about more transfer function stuff. We're going to come back next week. We're going to talk more about circuit design. Okay, so I hope everybody has a good week and we'll catch you later. See you.